So in previous videos, we have already drawn a free body diagram, come up with our reactions, and drawn the torque force diagram using a couple different methods for this simple problem, which is this rod, AD, which has a series of externally applied torques on it. So we're not going to go over that. I will leave some cards up here in case you want to go back and look at one or both of the videos that brought us to this point. But as our starting point for this problem, we're going to start understanding what the internal torques are over the entire length of AD as represented in our torque force diagram. So this problem is all about looking at the shear stresses that are going to be caused by the torsion in the shaft. So we're going to do a little bit of a quirk at it. We're going to look at this as if it was a solid shaft with a diameter of 50 millimeters, and we're also going to look at it as if it was a hollow shaft with an internal diameter of 40 millimeters and an external diameter of 60 millimeters. And so to be fair, so that's where I want to start. I want to look at the shaft and come up with the essential shaft properties that we're going to need when we go to look at the stresses resulting from torsion. And so that's called your polar moment of inertia. It's represented by J. And so what I need to do is for both of these shaft configurations, I need to be able to figure out what that is. So let's get started by calculate the polar moment of inertia. And so I'm going to identify these as A and B as we go through. A, the solid shaft, B, the hollow shaft as requested in the section. So in A then, for a solid shaft, we know, or we can look up the formula. We covered it, how this is derived, but it's pi over 2 and our radius, which we've been using C to match our textbook, to the fourth. And so that's the formula for the polar moment of inertia of a solid shaft. We can go right ahead and substitute in our values. So pi over 2 multiplied by C, which is the radius. So if 50 millimeters is the diameter, that means we have a radius of 25 millimeters. I want to work in meters to match the Newton meters in our torque force diagram. So I'm going to switch that and say 0.025 meters, all to the power of 4. And that gets me a value of 6.14 times 10 to the negative 7 meters to the fourth. And we'll do the same thing for our hollow shaft. So we'll go right on to B. J is equal to pi over 2. In this case, it's our C outer to the fourth minus our C inner to the fourth. So with our substitutions, again, switching to both meters and to radii instead of diameter. So we have 0.030, sorry, I should put in my units, meters to the fourth minus, what do we have, 0.020 meters to the fourth. And that would be equal to 1.021 times 10 to the minus 6 meters to the fourth. So that's great. So now we have our essential cross-sectional properties that we're going to need in order to look at shear stress. So let's have a look at what their formula is and see what we can do with it. So calculate our maximum shear stress. And so I'm going to underline that. So maximum shear stress. So the first thing we have to do is we have to look back at our torque force diagram and decide where is the maximum shear stress going to occur. And to be fair, we should annotate that. So the section that has the maximum torque is between A and B. We're not really concerned about the positive or the negative number. Remember, they only denote direction. And so when we're asking direction, we have to consider that. Otherwise, we're just looking for the absolute value of the magnitude, in which case 80. So between A and B at 80 Newton meters. So to be fully complete, though, when we're looking at the maximum shear stress doesn't happen uniform across the cross-section. As we were talking about previously, it happens at the most extreme fiber, at the outer part of this round circular shaft. So if I were to identify where this is occurring, I would say this is, you know, between A and B at outer fiber or at C. Now our formula for shear stress, so tau max is equal to T, C, which is our radius, all over our polar moment of inertia, J. And so we have these values now. We can substitute in. Now they're going to vary depending on whether we're looking at our solid shaft or our tube. So looking first at our solid shaft, so let's look at tau max is equal to our torque. Again, that's going to be 80 Newton meters. And our radius, so for the shaft is 25 millimeters or 0.025 meters. And we've calculated J, so we're going to substitute in 6.14 times 10 to the minus 7 meters to the fourth, and we get a value of 3.26 times 10 to the sixth pascals, which we know is the same as 3.26 megapascals. Going right along, we're going to calculate it for the hollow shaft. And so tau max, in this case, again, TC over J, and C in this case would be the C of the outer because it's the most extreme fiber. How far away can you get? So again, we have 80 Newton meters between A and B. We have a diameter to the extreme fiber of 30 millimeters or 0.030 meters divided by our polar moment of inertia for the hollow shaft, which is 1.021 times 10 to the minus 6 meters to the fourth. And we run those through our calculator, and we come up with a value of 2.35 times 10 to the sixth pascals, or 2.35 megapascals. Now, just as an aside, it's not asked for in the question, but if you wanted to figure out what the shear stress was at the inner face of the hollow shaft, all you would have to do is to change out your C value, or your diameter of 30 millimeters, to your inner radius. Usually we denote that by rho, and we would substitute in 20 millimeters or 0.020 meters for that, and you could figure out what that shear stress is at that distance. But I'm not going to go ahead and do that because it wasn't asked for in the question. So there was one thing I wanted to point out, and that's the efficiency of the hollow shaft. And by it's we haven't got there yet. We're going to get to the I-beam and flexure and everything else, and why that is so efficient in the use of material. But we'll get an early insight into that kind of thinking when it comes to the hollow shaft. So very quickly, I'm just going to calculate out what the areas are for my hollow or solid shaft and my hollow shaft, which is analogous to the amount of material needed to fabricate those two different structures. And so I'm just going to write it out here quickly. But what I wanted to point out in all of this is that the amount of area of the hollow shaft used in this instance is considerably less than what we used in the solid shaft. I mean, in effect, it's actually about 80% um, of what we used in the solid shaft. So the uh, material used, if you will, material used in the hollow was considerably less than the material used in the solid shaft. And at the same time, when we look at a comparison of the stresses resulting from it, we had considerably lower stress in the hollow shaft than the stress in the solid shaft. And so, despite the fact that we use considerably less material, we also resulted in considerably less stress. And this really does point to the efficiency of the tube as compared to the solid shaft. And, we can get into this later when we sort of plot it out and all that, and how we want to use our material most efficiently and effectively. But I wanted to show it here because we had the math sitting in front of us. So that's it as far as calculating shear stresses resulting from torsion in our simple shaft. And we're going to go from here. We're going to look at the deformations or the angle of twist resulting from it. So if you want to follow along, we'll have that link coming up here shortly. And we'll use exactly the same problem. So we're not going to redo a whole bunch of calculations. We're just going to go on and see how this particular shaft would deform as a result of the torques put on it. So I hope to see you back in that video.